pretty much have. Yeah, I'm literally. That's so nice. So we've got like a.
Yeah, just look at me and be ashamed. Okay, all right, so let's do this. Metric spaces. So the definition is from Rudin 2.15. And the definition goes a set X whose elements we shall, that's what Mr. Rudin says, we shall call points. Not like elements or terms we use for sequences. For this set X, we're going to call it call its elements points. And then this set X is said to be a metric space. So what is a metric space? It's a set. And the elements of the set we're going to call points. And then there's one other element to it. So before I get to the other important thing here, it's supposed to have a metric, a function, a distance function. Okay, so I'm going to draw the diagram here. This is our set X. And any point here, any dot here is a point, because we're basically looking at R2. So it's a plane, and then on a plane, you're going to have, because it's not 3D, 2 coordinates for this point right there. Okay, so a set X whose elements we shall call points, like this guy right there, which has a, so if I call that point, let's say P, then P is a point that has 2 coordinates, X and Y, but not necessarily. No, actually always, that's what I was thinking. Okay, okay, so metric space, if, and now this is the crucial condition, if with any 2 points, so I put one in, let me put another one here. Let's call that Q. So if with any 2 points, P and Q of the metric space X. So what's a metric space? It's a set, it has points, and it is a metric space if with any 2 points P and Q, we can define a function on that. So for any 2 points P and Q, there is an associated real number. The real number is usually just one thing, right? One number. And that number, we're calling it D, P, and Q. So we put in the 2 points to the function D, and it returns a real number. So this is a function. Let's just pretend we have the liberal arts people here. Jalen, you're liberal arts, right? Liberal arts, humanities? Oh, yeah. Okay. So this is a function. And then these are the 2 inputs, 2 points that the function D takes, and it spits out a real number. All right. And this real number So let's see, there is an associated real number called the distance. And this is how Rudin from P to Q. Such that, and then we have three conditions. So here's our P and Q. And this function here will allow us to calculate the length, the distance between these two guys. All right. So what is the first condition? The first condition is, let's call it A, the distance between P and Q such that, so if we put in these 2 points, what is returned better be positive. Because we're talking about distances. So a zero distance is non-negative, but we don't talk about negative distances. So in other words, this better be greater than 0. Okay. And especially if P is not equal to Q, which is true the way I've drawn those 2 points. But if P and Q are the same point, in other words, in our set X, if we took a point and did this to it to see what's the distance between P and itself, it better be equal to 0. So that could be like the base case, right? So the values of the distance start from 0 all the way to however large. Okay, next, this is the easy one. So the second condition is that if the distance metric between P and Q should equal the distance between Q and P. So it doesn't matter in what order you calculate. You can go from Q to P or from P to, which means that we'll be using absolute values on the metrics, and then Mr. Rudin, and then I've got all the. I'm gonna pause that. All right, number C. This is where I have to sit down because this one's the heavy one. It says it's basically the triangle inequality. So we go D is, so we're still with the 2 points P and Q we started. This should be less than or equal to, and it better be, if we have, so the distance between those 2 points on the whiteboard better be less than, let's see, P comma R. So we have R here. So this distance is going to be less than the distance between P and R, not necessarily unless we do plus distance of R to Q. So if you go from here to here, this distance better be bigger than going straight from P to Q. And you know what that does is it basically tells you you are in a plane. You're not on a number line. Maybe. Do you have any other, what do you think? Why is the third condition? I should have read this, but why is the third condition so important? Oh, in fact, okay. So what happens is later on we find out that sometimes this is easy to prove, this is easy to prove, and you better get this. If this is not working, then it's not a metric space. Do you think?
I guess it depends on what we're
Hmm.
doing. For some particular.
The reality of a plane. Right. Okay. And actually, where did I? Here, I'm gonna give you this. So because you are now too soft spoken, you need to be loud like me. Yeah, so just keep it on you. All right, let's go. So there's one last line we have to write. So I'm going to erase, I'm going to put the last line up here. So in your notes, it should go right after point number 3. And then Mr. Rudin, or actually Professor Rudin, says any function with these, any function with these 3 properties is called a distance function. Or a metric. Okay, so, all right, so a set X, a metric space is a set that has a distance function or a metric that works for that set, basically. Okay, so there is another way to represent all of this, which is, oh, it's not here. What you do is, I'll just do it right here. So this is a this thing is a metric space. You have the set first, and then the metric right there, or the distance function.
Is the set always R2?
No, it's RK.
Okay.
So RK, then you have R1, R2, and we usually just stay here.
Is it always with the field of real numbers?
Yes. Okay, very good questions. Let's move on. We're gonna skip. Well, we should not skip this. So let's look at an example of a metric space. And this is from some random PDF I downloaded from the internet. So this example, no, this is still root and example 2.6. And after that, we'll do 2 actual examples. And then we're going to move on to limit points and isolated points and all that business in open sets, which you guys probably do that in algebra open sets. Mm-hmm. Yeah, okay, good. All right, so so we have a Rudin example 2.16, and he says that the so I'm just going to write what the book had. The most important examples of metric spaces, or it's getting recorded. Yes, it is. All right, because I can mess that up. Are the Euclidean spaces are K. So where K can be, right, from 1 to. And so the first example of a metric space, example 1 of a metric space is R1. So that would be our number line, right? And here, and then here our distance formula would be, so this would be, so if this is, let's say, X here, and this is Y, then D, let's do P and Q again. P and Q, so 2 points on R, and here P's x coordinate. So this point here, its x coordinate is, let's call it P1. And its y coordinate, right? That's how we can call those actually numbers as points, right? That's my take on it. I mean, the books don't really specify that. And then we do P comma Q equals P minus Q. So these are absolute value signs. And then we could just use this standard way of, so I'm going to do the first coordinate minus, no, this is not going to work out, so I might have to delete it, people on the internet. I'm going to do P minus Q1 squared plus, no, that did not work out. Is that right? Will this work? And I'm doing, what did I do wrong here? Is there, this representation looks good to you, right? So we do P minus Q 0 minus 0. No, it doesn't work like that, does it? No.
No, it should. Because the
This will,
yeah, the second term will get removed, and then the square root of the.
oh, right. And then, yes, yes, very good. Okay, thank you. Because this will cancel with, okay, all right. And this is the same as that. So I'm just going to do this. So if the number inside the square is negative, it will become positive. It gets squared, but then the square root will bring it back to the actual distance. Very good. Okay. And this is again not in the books there. This is just you and me today. Okay. Next, we're going to do the second example is the distance. Example 2. And here we are going a little abstract of a metric. Is we could do R2. Should we do R2? Why not? Let's just do R2 because we have Jalen here. R2, and should we still stick with P and Q, or I'm going to go with X and Y. All right. And then this is in bold. So I'm going to say these are just basically vectors. This is not kosher. I can't do bold here. So I'm just putting arrows on top of that. Okay. So now we're in R2. And then this is, again, just in bold. All these are basically vectors because they have coordinates, 2 coordinates each. And then this formula will work beautifully with this. So I want to do is subtract the first coordinates of X and Y, and then subtract n squared, the second coordinates of these two, just like we did before. So we're going to have x1 minus y1 squared plus the second coordinate, because there are only 2 coordinates, r squared. And so we're going to have x2 minus y2 squared. And that's your formula. And these guys are not in bold. These are x1 and x2 are the coordinates of this guy. Yeah, and that is right. Okay, so in other words, this thing is actually x1 comma x2, and this thing is actually y1 and y2. Just in case. Okay. And then let's do the K1. And I think I'm going to skip that other thing. So let's have our third example is going to be RK. So And so if we were doing this, we would say what? R, the set itself is, I don't know if you do this, this is just me, and the metric would be just D here. It's an Euclidean metric. And that is the set that here. I've not seen that anywhere. That's just me. All right, let's go with our last example of a metric space. So here is our metric space Rk. So the set is going to be the set of real numbers. And so let's figure out the formula for the distance, the metric itself. So we have D. And here we just do this. So each one of these are, let me delete this here. Each one of these, sorry guys, are x1, x2, xk. And then this guy is y1, y2, yk. And therefore, what are we going to do? We're going to take the first coordinate of x and the vector x and the vector y, subtract them and square them, add, plus subtract the second coordinate of the vector x, x2, and the second coordinate of the vector y, and then subtract them and square them, and then plus the next coordinates, and then finally to the k. So here we go. We have x1 minus y1 squared plus x2 minus y2 squared dot 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 xk minus yk squared. All right, so we are now done with the metric spaces. I had two actual examples, people on the internet. We don't need the numbers. Okay, so let's start with so you've done this before, right? Somewhere? Yeah. Good review? Yeah. All right. Oh, this stuff, right? Yeah. Oh, yeah. Yeah. See, I never did multivariable calculus. Oh, yeah. It's I've kind of went through a course slightly with this guy on the internet, like just listening to him and taking notes.
A little fun, but it's
physics and also programming. Like if you're doing 3D shit, maybe.
I guess, but like linear algebra probably covers.
Which is basically an extension of
first part of calculus.
Yeah, yeah. So you like linear algebra classes, or?
I liked it.
Yeah. Okay. Because you did the proof-based one, right?
Right.
Yeah. All righty. Now we are still on Rudin. This is definition 2.17. And we are now defining what is an open, and then this is just me, closed ball, which is basically the neighborhood thing that we've been looking at in the class. So if you have a point or a number x, so this has to be a point, right? And it will have coordinates. So if you have an element, a point from Rk and a radius r, so this is just a length, and this is a point. By point, we mean that you could do that, but I shouldn't, but I don't know how to do the bold thing. Okay, so if you have this situation, we have a point in Rk. So let's make the point right here. And then it says, if we have a length r, let's throw that in. Oh, this is dead. And so, and we are in a, right, it could, and we're just doing, we're representing what would happen if there were k dimensions by just doing the picture in 2 dimensions. And then you let the computer do the rest. Okay, so we have a point x in Rk, or in our case, our Rk is, just for sake of simplicity, in 2D. And then we have a length, this length here, which will be the same in all dimensions. It's just going to be a length, right? Okay. D, so the definition is D open or closed ball B with center X at, with center at X, sorry, and radius R is defined. So let's do that. So we have a ball that's supposed to be round. And let's draw another one here, actually up here. We have a second ball here with the same radius R. And so this is an example of an open ball because the points on the boundary are not included in this neighborhood or in this ball. And then we have a closed ball right here. Where every point here is also included in this ball or neighborhood. And that's what I'm going to say right now. So it goes on to say, is defined to be the set of all y. So we have all y that belong to. So that means this y could just be a number on a real line. This y could be an ordered pair. This y could be with 3 coordinates all the way up to x coordinates, right? Okay. Such that, and the key definition, such that the where is that? Such that y minus x. So where are our y's? We got a, let's do, there's a y right here. Got another y right here. We have a y here. And then for our closed ball, we have y's on the boundary, on the circle, here. So the distance from all y in the closed ball from x, which is the center point, the distance of all y's, and in the open ball, the y cannot be a point on the boundary, on the circle, is obviously, here comes the exciting part, maybe not, is less than r, or so this would go with and this guy would go with that right then. So this is how Mr. Rudin describes it. And we just did that, right? How do we expand that? We just did that. Square root, and then first coordinate minus the first coordinate of the second point, squared plus second coordinate is subtracted from each other difference, squared plus all the way to k. And here, every distance between each of these guys is less than or equal to r. Here, every distance from y to x better be less than r. This guy. Okay. Should I? Yeah, I'll do another definition of the same idea. And then this is from a professor who used to teach at Harvey Mudd. Is this the Harvey Mudd guy? Yeah, it is. Francis Su. So he's I read his bio. He was at Harvard, and then his supervisor said that you're not good enough. So when they tell you that, it means it's not you, it's them. So then, in the middle of his work, he had to switch fields and get another supervisor, and became a successful mathematician in another field of mathematics. But because of his troubles with math, he's a great teacher. Because if you're too smart, you don't know where the problems are. And so he put these that I've been watching for this class that I'm teaching. I'm basically using his notes and Rudin's definitions as well. So according to his definition, so we'll write Francis Su. All right. And I think he's now my age. The videos were when he was younger. So we are defining open ball, according to Francis Su, which is probably from textbooks, obviously. He also calls the open ball neighborhood, and he does this BHH, neighborhood. NBHT, it's very useful, neighborhood. And then he says, he actually puts neighborhood on top of this guy here. A ball is a neighborhood. Why are we using the word ball? Because we are in 2D and higher. If you're on a real number line, it's just a neighborhood, right? So if you're like this is, let's say this is the center point R, and then x minus R and x plus R. This thing is called a neighborhood. Just like yesterday's class when we had, it was inside that epsilon neighborhood where all the terms were clustering. So, and then if you're in 3D, we just saw that picture, right? The circle. Okay, so this is for 1D, and we don't usually call that a ball, but I think we can probably. Because the definition fits. The R goes to the right and to the left, right? And that's the only place. While in 2D, the R's are all around, right? Okay, so so the neighborhood thing comes in here with M. Is that one of? No, that's the professor. So this is saying the neighborhood with radius R centered on X. This is radius. The length centered on X, the center point, equals, you can say it like that. You can also say it like this. We have a ball centered on that with radius R. We have a neighborhood centered on X with radius R. And this equals, and what is this neighborhood? It is the set of all Y's, just like we did just now, right? In the older definition, the open or closed ball was a set of Y's that were within R distance of the center point X. And so here we are doing, so here we can bring in a metric the distance formula or the distance metric. And this better be, so sorry, y, so the ball is the neighborhood or a circle that contains all the y's that are within or equal to the radius r. Okay, and so let's just make a quick picture here just for sake of pictures so that you will never forget this lecture ever. R right there. And this is in our illustration. We're using 2D. And this is the metric here is Euclid, Euclidean metric.
Should just be
No, both.
for open.
Oh, yeah, I did that.
I don't know what you were trying.
I would have just one definition, but no, you're right. Let's do this. Closed ball. Again, this is good. And then R, same. Neighborhood around X, a radius R equals B. And this is what the professor does. He puts a line on top of it to show it's a closed ball. And then there's no line here. And then he does what you just told me to fix, which is less than or equal to R. All points Y that are inside the circle in the ball, including all the points of the boundary because of this equal to. Okay, let's move on. Or we can take a break, pizza break, or should we keep going? Oh, drink. Okay, let's do the, I'm gonna pause this and then somebody, and there's bathrooms right outside, and somebody needs to tell me to unpause it, as in resume. Some of us can't pronounce it. Resume. Ooh. So that this spills right into that. That would be brilliant. Or I could sit on that. Okay, now we're moving on to basically points. Remember that a metric space X and the elements of a metric space are called points. So now we have to think about what points are and their properties, and that's what we're doing. And different points, these elements of the metric space have definitions. They have been defined and people talk about them. So when you hear, so our first definition, this is also from Rudin. So it's 218b. And I forget what A is, but maybe we'll get to it. This is, we're defining this guy here, limit point. Let's say limit point for a set. And key thing is that the limit point doesn't have to belong to the set, but it is a limit point for that set, okay? So for instance, before I get in, I'm gonna do this and then I'm going to use Francis Su's diagrams. Here, the whole point about the limit point is that it doesn't have to be a member of that set. So for instance, if this is, let's say, a set, actually, let me make a square kind of looking set, right? Kind of like what Professor Su would do. What kind of, whatever this thing is, it's, the boundary points are not in the set, right? So let's pick this point here. And actually, I'm going to, this is actually the way his diagram looks like. Here's Mr. C right there. And let's call this set E. C is a limit point of set E because if I draw a ball around it, they're always in that ball, however small that ball is, as in however small the R is, very, very tiny R, this ball, this neighborhood will catch other points. Let's call these other points Q's. It will always have Q's in its neighborhood. It's going to have, C is going to have points from outside of the set E, and the point C will have in its neighborhood, the ball around C points from set E. This is a limit point. So the whole idea is that the limit point is very, very, this thing shows up in so many places. And you really have to, is that the elements of E are piling up to that point that doesn't even belong to that. So in other words, we have a set E, and we choose a sequence of points in set E. Let's do that. I have A1 here. I have another A2. We have A3. I'm going to hit A uppercase capital N, the threshold point. And after that, let's see. Where is this sequence going towards? Yes, sir. So C is the limit of the sequence, which, so we chose a sequence from set E. We chose a bunch of points. We're calling it a sequence E from the set E, and they went all the way towards our limit point. So this sequence has a limit point. It is its limit. So that is what's going on here. So this is our sequence that we chose, and it tends towards, it piles on towards C. Okay, all right. Let me put, what if I did this? So now we have a set E in which one of the boundaries of set E is a solid line, which means it's a closed boundary. This is an open boundary. Is set C an element of E? And the answer is no, because it's on the open boundary. All points on the open boundary are not members of the set that boundary forms. Now I'm going to put, and I'm again using another point here. That's our professor calls it A. Is A an element of E? Jalen. And I think you are right. It is an element for the recording. Yes, very good, Jalen. It is an element of E because it's on that solid line, which means we're talking about a closed boundary. And then this is an open boundary. Open boundary points do not belong to the set E. Points on the closed boundary do. I think if on a real number line, you will have something like this, right? Let's say this is 2 and this is 5. 0 is here. 2 is included. This is the closed side, and this is the open side, where 5 is not included in the set E here. Question?
Yeah, this makes a lot more sense because I was reading something the other day about matrix Liger. And it was talking about basically like the general linear group. It's a group that contains all invertible
Mm-hmm.
And it was talking about how it's closed if for any sequence within or within like
You choose a sequence from the
Right.
matrices.
And if
Yeah.
any sequence
It's
has a limit of A, then A is or it's not inverted.
yeah,
So it's,
same thing. So the cool thing about math is these concepts just show up everywhere,
right.
and you just have to learn them once, forever, so that when they show up again, you can quickly recognize. And because your understanding of the simpler situation is easy, because you didn't see this before, you're seeing it in a very complicated picture, which now is getting clearer because we're looking at a very simple picture, right?
Right, because there's no geometry.
Yeah.
No. With matrix.
No. Oh yeah, that's right.
Right. Right.
Oh yeah. Yeah, there is that.
Yeah, I don't think the analysis class I took covered this sort of definition of
Yeah.
what's that?
Yeah. You should take I don't know. You could always just take a graduate level real analysis class and get great. Yeah. I don't know if I should recommend that, but okay. So I'm going to delete this. And then let's do a couple of other points. We have, okay, so first we're saying A is an element of E. C is not an element of E. Not, yeah, C is not an element of E, E, but C is a, let me write these guys here. So C is not an element of set E, but C is a limit point. And why is it a limit point? Because if we found a sequence inside the set E, and if that sequence tends towards that, that's the application of that. But the definition of why C is a limit point, so sometimes the definitions don't really give us its use value. Okay, like why is the concept of limit points important? It's the how we use it. Now let's look at A. A is an element of E. A is it a limit point? So we apply the definition. The definition is that if we draw a ball or neighborhood around A, and in that neighborhood we find other points from that set E, then the point A, which in this case belongs to set E, is a limit point for E. So here we go. So A is a limit point because if we draw a circle around it, it will capture, it will include, and however small you do it, it's going to have points from set E. All right. Now we're going to look at a point that is by definition a limit point, but we don't really care about it. The limit points that we are interested in, as Ryan just mentioned, are the ones that are on the boundary of the set. This one and this one. I'm going to put another point right here where our good professor puts it, and B. So is B, this is for Jalen, is B an element of E? Point B. Because it's inside that little, it's inside this thing, right? So it is. Yeah. It's inside. In fact, it's called a interior point. It's in the interior, the hinterlands. And the definition of interior points, let's just do that quickly. So, okay, so B is an element of E. B is also called, B is a interior point. I'm going to go over the definition of interior point as soon as we get there. I actually have the definition from Rudin. Interior point, how do you define an interior point? If I make, let's say B was actually right here. Can I make, so B is right here. Is B an interior point? And the definition tells us B is an interior point. It looks like it's on the, what is it? It's on the right where the border with Russia starts, right? So if E was Ukraine, oh, this shit, I should not be joking about that. I'll get fired. So here we go. We have, if I draw a ball around B And if that ball is contained within the set E, then point B is an interior point. I'm going to draw. Yeah, I got that right. What if I put the point B right on, if B was here on the open boundary, is it? So in other words, all the points in the neighborhood of B better be in the set E. That's the definition. Here we just want some points to be in E. Because, and this is not an interior point because they're points that are outside of the set that are in that neighborhood. So B is, this second B that I just drew is a limit point. What if I made B very close to a boundary? Let's say my B is right here. Can I still make a circle, a ball around it? Yes, because we are dealing with real numbers. There's infinitely many numbers between B and the solid line here. Okay, so that's what an interior point is. But, so I'm gonna put my B back where the professor put it. And now the question is B a limit point? And how do we check that? We just apply the definition, and the definition is that if I drew a very small neighborhood, a very small ball, or a very big ball with a large radius, B, that neighborhood should capture some points that are in E, and it does. So the same definition makes an interior point. Sorry, what am I talking about here? Sorry, the limit. The definition of limit is fulfilled by the interior point, but this is an interior point that is uninteresting. Uninteresting. So B, as it's placed right in the interior of the set, B is a uninteresting limit point, while A and C are. Okay, all right. So what happens is the same definition, two different definitions works for the same point. One definition calls it an interior point. Okay, so the limit point definition says this is a limit point. The interior point definition also calls it a limit. The interior point definition works for this point B. The limit point definition also works for the same. Okay, that's what I was trying to say. All right, now let's so I think the next definition after this is we're going to do interior point. I'm going to now give you the Rudin's definition of what a limit point is. So B, so 218B, he says a point, and we are all in a, this whole thing is in a metric space, for instance, right? Or in fact, E could be seen as, E is a set in the metric space. Okay, so if a point P is a limit point of the set E, so limit point definition of a set E, and we have two examples here, A and C. If every neighborhood, however small or big, right, of this point P, which we are, right now point P is a candidate limit point. If it satisfies this is where the condition comes in. This is the condition line here. If it satisfies the condition, then we can call point P a limit point. that the neighborhood of P contains a point and all it needs is just one point Q. And I've been talking about containing other points, but just all it needs is one such that this point that is in the neighborhood is not the same as our limit point P. Actually, it does Q is not equal to P. What did I messed this up. Let's see. So P contains a point Q that is not equal to P such that Q, this is the key condition, belongs to P, which is what I have been saying. Okay. All right. And I think another the word that I came up with is that a limit point is relevant because of what's in its neighborhood. So it's the nearby is limit point is the nearby thing. It's the where it actually is becomes important. So because this is topology, because you're talking about what is near and what is far away, right? I'm going to throw in another point here, W. And I'm going to say that W is not an element of, W is here, and it is not an element of E. So I'm going to define it right here. Because I could say that W is an element, right? You have a giant blob over there and then an isolated point here. So W is, let's see, is that? Where is W? W is not a member. And then is W that's the question I'm asking. Is W a limit point? No, because it is if I drew the ball this big, but it is not true for every ball, for every radius that it's going to have some Q from E. So this is not a limit point. So not a limit point. And then I have another point here. Let's say, let's call it E. And I'm going to say that E is an element of set E. Small e is an element of set E. Is E a limit point? No. So just like C was not an element of E, but was a limit point, A was an element of E and was a limit point. W, which is not an element of E, fails to become a limit point, and an element, an isolated, and so this is an isolated point. And I don't know the definition yet because it's on the next slide. Let's see, should I say anything else here? Open boundary points are, we just did that. Open boundary points are not members of the element. These points are not in the set E. Closed boundary points are elements of E. So let's move on. I think we can now move on. Should I say anything else? No, I think we're good. You gotta run? Okay. And then whenever you need to run, you also tell me. Let's keep going. And thank you, Jalen.
Yeah, I'll get you that email today.
Yeah, to that Bobby guy.
Yeah, I'll get you.
Yeah. Oh, you better not watch this video. You're talking about Bobby. Okay, let's do should we do interior? Let's do isolated and then we'll do interior. Because that's the order I have here. All right, so next is, so, and again, any of this stuff you might see in what you're doing right now in your classes. Because there's only a finite number of relationships that things have with each other. And the things change, the relationships don't.
Right. I'm not in analysis right now. The thing I was reading is
Mhm.
it was like an American something publication, which is for fun about something with like particle physics. I don't know.
So the question is, are pure mathematicians, Terence Tao, a good example is Einstein versus, what was that guy? The guy, Hilbert. No, not Hilbert. Hilbert spaces, you might have heard.
I've heard of them. I haven't
So
seen them.
Hilbert came up with the plan for 20th century math, right? He's like, we need to do this. And I think it was Hilbert or Poincaré who was a mathematician. And they were really right there with Einstein figuring out how the universe works.
Yeah.
Einstein's math wasn't that strong.
Yeah.
So he was
That's-
freaking out. If you watch documentaries that I used to do, Einstein's like, oh no, it's my idea.
Yeah.
And so
Yeah,
Hmm.
he had to do like learn differential
because he had to,
geometry.
and he was not good at mathematics, but
Yeah.
intuitively he's like a genius
Yeah,
forever.
perfect.
And so there were people smarter than Einstein, but they were in
Yeah.
the mathematics department. All right, let's do isolated point, which is definition 218C, again from Rudin. Isolated point, and oh, wait a second, here it is. So actually one thing that I didn't write, I'm gonna write this time. So every time we are doing this definition, we assume these things to be true. So let X be a metric space. So just like for the limit point definition, I forgot to write this, but we should always have this in mind. I kind of mentioned this. Let X be a metric space. And then I think that's it. And then everything will be element of, all the points and things will be, sets of points will be elements of X. All right, so the definition goes, of isolated point if P belongs to E. Okay, so if P is an element of E and P is not, and this is Rudin, I didn't write this weird definition, not a limit point of E, then, so let's do that. Let's draw that same picture. So we have a P that is an element of E, and if P is not a limit point of E, then P is called a isolated point. So let's do, oh, let's have the same Francis Su looking set E here. So this is our set E, and it's in the metric space X. So P is an element of E, and P is not a limit point of E. Okay. So where can we put P? Number one, can we put P on the open boundary? Because if it did, it would be a limit point. So we can't, right? And also it says P better be an element of E. So this is out for sure. Because all the points on the open boundary are not elements of E, we can't, so let's stick it here. Now, this satisfies this bit, but it fails because here P will be a limit point. So what if we put P inside right here? Would that work? Yes, it satisfies this part, but doesn't satisfy that because it's a limit point.
Silly, or not silly, but
We're trying to locate where to put it in the picture
right.
by just looking at these two. So therefore, P better be outside.
Seems
Go ahead.
frustrating that they don't just define it as like a point such that
Right.
exists in neighborhood in which that does not contain any.
Because that would make math accessible.
Yeah, it's like the definition of compactness.
Yeah, yeah.
Are you?
Yes, yeah. Compact sets, yes.
Yeah.
And
then
I think the
Heinz-Borel is-
reason is people have tried those definitions, and the definition has to be kind of like a committee definition,
Yeah,
so that it doesn't piss off everybody.
I
it-
guess.
Yeah,
I don't know.
there has to be rigorous reasons why this is done like this.
Sure. I'm sure like the first proof people do with this is proving that the definition I just gave is equivalent to this. Because I feel like it's much more useful.
Yeah.
But there are cases in which the definition of compactness is
Hmm.
also useful. It was interesting. I had the worst textbook of all time. The only example they gave proving something was compact using its definition was proving that a set of finite points is compact. And then the thing on the homework was like, if something is a closed subset, or if A is a closed subset of B and B is a compact set, prove that A is a compact set using the definition of compactness. And you have to like concatenate the any open set you have for B along with the, I don't know what the term is, all the real numbers except for A. And then you have a set.
It's I think it's the open a neighborhood with a hole.
No, it's like the so if you have like a closed set A,
But go ahead.
everything except for
Right.
A.
Okay.
Yeah. Yeah, and so you union that, or well, so you take any open family or any open cover for B, and then you union that with the open set that is everything except for A, so R minus A or whatever.
You're right.
And then you have that family of an open cover, and then since B is compact, it means you can find a finite set of that will cover B. Since you can find a finite set that covers B, you can find a finite set that covers B. Something along those lines.
Oh my.
And it was
because the definitions are not useful, but they are perfectly correct.
right.
No, yeah. You can't. This is a definition you can't mess with.
Yeah.
But maybe there's going to be another professor called Rudin who shows up and gives us a
Sure,
one of the things actually before so you're going to have those things right in there. I'm going to tell you something else. So I have to pause. So resume. Okay, they gave up. They didn't have access to it. Okay, all right. So let's do this again. So if P is E, if P is in E and P is not a limit point, then what we figured out was that it has to be outside here. And now the next if these two conditions are true, which is now represented by this picture here with P outside of the set E in the metric space X, then Mr. Rudin then goes on to say that if these two conditions hold, then let's see, P is called an isolated point. And I just want to, again, I want to give a picture here in 1D. And the picture here is, let's say we have a set here. Let's call this set E. And let's just go over that same thing that you were saying I shouldn't be doing. Again, P is in E, so it needs to be here. And P is not a limit point. So if P was on the closed boundary, or what is it actually called? The in an interval, what do we call that? The endpoint, right? Oh. Is it a closed endpoint and an open endpoint, right? how do we do that? So our set E is in blue, and therefore it needs to be the point P. This is also part of with our color coding here. And now we can say that P is an element of E, yes, because it's in blue and it's a dot right there. So this interval plus the union of this point is our set E, right? So it's and then P is not a limit point because it's not on the open boundary or in the closed boundary or inside. Any point inside, on the closed boundary and on the open boundary is a limit point. And that's our illustration for R1. And we are done for today. Cool. I think